Photon sphere, the strange place where light cannot escape. A journey to the edge of physics, where even light itself must orbit. Welcome to another exploration of the cosmos on the event horizon of sleep. Find a comfortable position, let your breathing slow, and prepare yourself for a profound journey across space and time. Tonight, we're going to journey to one of the most extraordinary places in the universe, a place where the rules that govern our everyday experience completely break down, a place where the fastest thing in existence, light itself, can become trapped in an eternal circular prison. We're going to explore the photon sphere, a boundary surrounding black holes where gravity has become so impossibly powerful that even photons, the messengers of illumination that have traveled freely across the cosmos for billions of years, can be captured and forced to orbit endlessly in the darkness. When you look up at the night sky, you're bathed in ancient light, photons that have traveled unimpeded across unimaginable distances, crossing the void between stars and galaxies, finally terminating their journey in the depths of your eyes. Light seems unstoppable, doesn't it? Nothing is faster. Nothing else can claim such freedom of movement across the universe, and yet there exist places so extreme, so fundamentally warped in their nature, that light itself becomes a prisoner. The photon sphere is one of those places. It exists just outside the event horizon of a black hole, at a very specific distance from the center of that cosmic abyss. At this precise radius, gravity exerts exactly the right pull to bend light into a circular path, not pulling it in completely, not letting it escape, but holding it in an unstable orbit. A photon that enters this region with the right trajectory will circle the black hole, potentially forever, never falling in, never breaking free. This is a journey that will take us through some of the most profound ideas in physics. We'll explore the nature of light itself, the revolutionary insights of Albert Einstein, the tragic genius of Carl Schwarzschild, who first calculated these phenomena from a World War I battlefield, and the incredible modern observations that have finally allowed us to see the shadows cast by these cosmic monsters. Along the way, we'll encounter concepts that challenge our intuitions about space, time, and the very fabric of reality. The photon sphere is more than just an interesting astronomical phenomenon. It represents one of the most extreme environments in the known universe. Understanding it requires us to abandon our comfortable notions of how the world works and embrace the strange, beautiful, and sometimes terrifying predictions of general relativity. It asks us to imagine what happens when mass becomes so concentrated that it fundamentally alters the geometry of spacetime itself. If you enjoy these deep explorations of the cosmos, these meditative journeys into the mysteries of existence, a quick like or subscribe would truly help the channel grow. Your support allows these nocturnal expeditions to continue. Now, settle in, let your breathing slow, and prepare yourself for a voyage to the edge of physics, to a place where light cannot escape. Before we can understand what happens to light near a black hole, we need to understand light itself. What is this phenomenon that illuminates our universe, that carries information across cosmic distances, that allows us to perceive the world around us? The answer is both elegantly simple and profoundly mysterious. Light is electromagnetic radiation. It's a self-propagating wave of oscillating electric and magnetic fields that travels through the vacuum of space at approximately 299,792 458 meters per second, or roughly 300,000 kilometers per second if we round slightly. This is what physicists call the speed of light, denoted by the letter c, and it represents the universal speed limit of our cosmos. Nothing carrying information or mass can travel faster than this. To put this speed in perspective, light can circle the entire Earth approximately 7.5 times in a single second. It takes about 1.28 seconds for light to travel from Earth to the Moon. From the Sun to Earth, the journey takes roughly 8 minutes and 20 seconds. When you look at the Sun, you're seeing it as it was over 8 minutes ago. In a very real sense, we're always looking into the past when we observe anything in the universe, because the light carrying that information took time to reach us. The nature of light puzzled scientists and philosophers for centuries. Is light made of particles, tiny corpuscles streaming from luminous objects? Or is it a wave, like ripples on a pond, propagating through some mysterious medium? The answer, as quantum mechanics would eventually reveal, is both. Light exhibits what physicists call wave-particle duality. In certain experiments, light behaves exactly like a wave, demonstrating interference and diffraction patterns. In other experiments, light behaves like discrete particles, packets of energy called photons. Each photon carries a specific amount of energy related to its frequency. Higher frequency light, like ultraviolet or X-rays, consists of more energetic photons. Lower frequency light, like infrared or radio waves, consists of less energetic photons. The visible light that our eyes can detect occupies a narrow band in this vast electromagnetic spectrum, ranging from the lower energy red wavelengths to the higher energy violet wavelengths. A single photon has no rest mass. It exists only in motion, always traveling at the speed of light in vacuum. This is a crucial point for understanding what happens near black holes. Because photons are massless, you might think gravity shouldn't affect them. After all, in Newton's conception of gravity, gravitational force depends on mass. An object with zero mass should experience zero gravitational force. But this is precisely where Einstein's revolutionary insight comes into play. In general relativity, gravity isn't a force at all, at least not in the traditional sense. Gravity is the curvature of spacetime, caused by the presence of mass and energy. Objects don't fall because a force pulls them downward. They fall because they're following the straightest possible paths through curved spacetime, what physicists call geodesics. And here's the key insight. This applies to everything, including massless photons. Light follows the curvature of spacetime. When spacetime is curved by a massive object, light bends around that object. This was one of the first predictions of general relativity to be experimentally confirmed, and it fundamentally changed our understanding of both light and gravity. In 1919, British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During totality, when the moon blocked the sun's blinding disk, Eddington photographed stars whose light passed close to the sun on its way to Earth. He compared the apparent positions of these stars during the eclipse with their positions when the sun was elsewhere in the sky. The results showed that the starlight had been deflected exactly as Einstein predicted, by about 1.75 arcseconds for light grazing the sun's edge. This observation made Einstein world famous and established general relativity as the correct theory of gravity. The announcement that starlight was bent by the sun's gravity captured the public imagination and appeared in newspapers around the world. Einstein, previously known mainly within academic circles, became an international celebrity overnight. The story of Eddington's expedition is one of science's great adventures. The eclipse was visible from two locations: the island of Principe off the coast of Africa, where Eddington himself observed, and Sobral in Brazil, where another team took measurements. Weather threatened to ruin the observations at both sites. At Principe, clouds parted just in time to capture the crucial photographs. At Sobral, some of the photographs were affected by instrumental problems, though others succeeded. The analysis of the photographs took months. The apparent positions of the stars near the sun had to be compared with reference photographs taken when the sun was elsewhere in the sky. The deflections were tiny, barely detectable with the photographic technology of the time. But when the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in November 1919, they confirmed Einstein's prediction and refuted Newton's theory, which had predicted a deflection only half as large. This tiny deflection caused by our sun hints at what happens near much more massive objects. The more mass, the more space-time curves. The more space-time curves, the more light bends. And when mass becomes concentrated enough, when it collapses into a black hole, the curvature becomes so extreme that light can be bent into closed loops, orbiting endlessly in what we call the photon sphere. The century since Eddington's expedition has seen general relativity tested with ever-increasing precision. Gravitational redshift has been measured with atomic clocks at different altitudes. The precession of Mercury's orbit, one of the original puzzles that motivated Einstein's work, has been verified to match general relativity. Binary pulsars, pairs of neutron stars orbiting each other, provide laboratories for testing relativistic effects, including gravitational radiation. Every test has confirmed Einstein's theory. The predictions of general relativity, including the existence of black holes and their photon spheres, have been vindicated by observation after observation. The theory that seemed so abstract and mathematical when Einstein first proposed it has proven to describe the real universe with extraordinary accuracy. The story of how we came to understand these cosmic phenomena is inseparable from the story of one of the greatest intellectual revolutions in human history, Albert Einstein's general theory of relativity. To understand the photon sphere, we must first understand the radical reconception of space, time, and gravity that Einstein gave to the world. In the early years of the 20th century, physics was in crisis. The classical mechanics of Isaac Newton had reigned supreme for over 200 years, explaining everything from falling apples to the orbits of planets with remarkable precision. But cracks were appearing in this venerable edifice. The behavior of light, the nature of electromagnetism, and certain anomalies in the orbit of Mercury all suggested that something was missing from our understanding. Einstein began his revolution in 1905 with the special theory of relativity. This theory addressed the relationship between space and time for observers moving at constant velocities relative to each other. Its implications were stunning. Time is not absolute, but passes at different rates for observers in relative motion. Space contracts in the direction of motion. Mass and energy are equivalent, related by the famous equation E equals mc squared. And most relevant for our purposes, the speed of light is constant for all observers, regardless of their motion. But special relativity had a significant limitation. It only applied to frames of reference in uniform motion, not to accelerating frames or systems affected by gravity. Einstein spent the next decade wrestling with this problem, and the result was his masterwork, the general theory of relativity, completed in 1915. The key insight of general relativity is what Einstein called the happiest thought of his life. He realized that an observer in a sealed box, falling freely in a gravitational field, cannot distinguish their situation from being in deep space, far from any gravitating body. An astronaut in orbit around Earth is in continuous free fall, and inside their spacecraft, they experience weightlessness identical to what they would experience in the absence of any gravity. Conversely, an observer accelerating in deep space, far from any massive objects, experiences effects indistinguishable from being at rest in a gravitational field. Stand on a spaceship accelerating at 9.8 meters per second squared, and you would feel exactly the same as you do standing on Earth's surface. This equivalence between gravity and acceleration led Einstein to a profound conclusion. Gravity isn't a force acting at a distance, as Newton had conceived it. Instead, gravity is the geometry of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells matter and energy how to move. Imagine spacetime as a stretchy fabric, like a rubber sheet. If you place a bowling ball on this sheet, it creates a depression, a curvature. If you then roll a marble across the sheet, the marble's path will curve toward the bowling ball, not because the bowling ball is pulling on it with some mysterious force, but because the marble is following the curved geometry of the sheet. This is a simplified analogy, of course. Real space-time is four-dimensional, not two-dimensional like a rubber sheet. And the curvature involves both space and time, not just space alone. But the essential idea holds. Massive objects curve the space-time around them, and other objects, including light, follow the resulting curved paths. Einstein's field equations describe exactly how mass and energy curve space-time. These equations are notoriously complex, a system of 10 coupled nonlinear partial differential equations. Einstein himself doubted that exact solutions would ever be found, but he was proven wrong, almost immediately, by a brilliant physicist working under the most trying circumstances imaginable. The first exact solution to Einstein's field equations came from Carl Schwarzschild, and his story is one of the most poignant in the history of physics. Born in Frankfurt, Germany on October 9, 1873, Schwarzschild displayed exceptional mathematical ability from an early age. At just 16 years old, he published his first scientific paper on the theory of celestial orbits. Schwarzschild pursued his studies at the universities of Strasbourg and Munich, earning his doctorate in 1896. He rose rapidly through the academic ranks, becoming director of the Göttingen Observatory in 1901, and later in 1909, director of the Astrophysical Observatory in Potsdam, one of the most prestigious positions in European astronomy. His work spanned a remarkable range of subjects. He made fundamental contributions to the study of stellar atmospheres, photographic photometry, and the physics of radiation. He was equally comfortable with observation and theory, with mathematical abstraction and practical instrumentation. His colleagues described him as possessing both a warm personality inherited from his mother and an immense capacity for sustained hard work from his father. When World War I erupted in 1914, Schwarzschild was 40 years old, well past the age of conscription. Nevertheless, driven by patriotic sentiment, he volunteered for the German army. He served first on the Western Front in Belgium and France, then was transferred to the Eastern Front in Russia. Despite the chaos of war, he continued his scientific work, calculating artillery trajectories by day and contemplating the cosmos by night. It was there, in the frozen trenches of the Russian front, amid the thunder of artillery and the horror of mechanized warfare, that Schwarzschild received copies of Einstein's newly published papers on general relativity. Einstein had presented his field equations to the Prussian Academy of Sciences in November 1915. Within weeks, Schwarzschild, serving as a lieutenant in the German artillery, had found the first exact solution. Schwarzschild considered the simplest possible case: the gravitational field surrounding a single spherically symmetric, non-rotating, uncharged mass. He derived the precise mathematical description of how spacetime curves around such an object. On December 22, 1915, he wrote to Einstein, including his solution in the letter. He concluded with the words, "As you see, the war is kindly disposed toward me, allowing me, despite fierce gunfire, at a decidedly terrestrial distance, to take this walk into this your land of ideas." Einstein was delighted. He had not expected that anyone could find an exact solution to his complex equations so quickly or so elegantly. He presented Schwarzschild's work to the Prussian Academy in January 1916 and arranged for its publication. The Schwarzschild solution revealed something extraordinary. At a certain radius from the center of the mass, the mathematical description of spacetime became singular, meaning some of the terms in the equations became infinite. This radius, which we now call the Schwarzschild radius, defines the size of what we know as the event horizon of a black hole. For an object of mass m, the Schwarzschild radius is given by the formula Rs equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. For the Sun, this radius is approximately 2.95 kilometers. For the Earth, it's merely 8.87 millimeters, roughly the size of a marble. If you could somehow compress the entire Earth to within that tiny radius, it would become a black hole. Schwarzschild himself regarded this finding as a mathematical curiosity with no practical relevance. He did not believe that nature would ever produce objects dense enough to collapse within their Schwarzschild radii. This was a common view among physicists of the time. Even Einstein himself, decades later, wrote a paper attempting to prove that black holes could not form through natural processes. Tragically, Schwarzschild would not live to see his work's ultimate significance. While serving in Russia, he contracted pemphigus, a rare and devastating autoimmune disease in which the body's immune system attacks the skin, causing painful blistering. In Schwarzschild's time, there was no treatment. He was invalided home in March 1916 and died just 2 months later on May 11, 1916, at the age of 42. He left behind a grieving family, including his son Martin, who would later become a distinguished astrophysicist at Princeton University. His daughter Agathe immigrated to New Zealand and became a classics professor. His son Alfred, tragically, remained in Nazi Germany and was murdered during the Holocaust in 1944. But Karl Schwarzschild's scientific legacy endures. The solution that bears his name is as fundamental to the study of black holes as Coulomb's law is to electricity. Every discussion of event horizons, singularities, and yes, photon spheres ultimately traces back to those calculations performed in the trenches of World War I by a dying man who found beauty and meaning in the geometry of the cosmos, even amid humanity's darkest hours. How black holes form. The formation of black holes is one of the most dramatic processes in astrophysics, the ultimate triumph of gravity over all other forces. To understand how photon spheres come to exist, we must understand how the black holes they surround are born. Stars spend most of their lives in a delicate balance. Gravity pulls the star's matter inward, trying to compress it ever smaller. But nuclear fusion in the star's core generates tremendous heat and pressure, pushing outward and supporting the star against gravitational collapse. This equilibrium can last billions of years for stars like our Sun, or merely millions of years for the most massive stars. The fuel for nuclear fusion is finite. A star begins by fusing hydrogen into helium in its core. When the hydrogen runs out, the core contracts and heats up, eventually reaching temperatures high enough to fuse helium into carbon and oxygen. More massive stars continue this process, building up successive shells of fusion around an increasingly dense core. Carbon fuses to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. Iron is a dead end. Unlike all previous fusion reactions, fusing iron absorbs energy rather than releasing it. When a massive star develops an iron core, it has reached the end of its nuclear burning life. Without the outward pressure from energy-generating fusion, the core has nothing to resist gravitational collapse. What happens next depends on the star's mass. For stars with cores between about 1.4 and 3 solar masses, the collapse halts when the core reaches nuclear densities. At these incredible densities, electrons are forced to combine with protons, forming neutrons and releasing a flood of neutrinos. The resulting object is a neutron star, supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect related to the Pauli exclusion principle. But for stars with cores exceeding roughly 3 solar masses, even neutron degeneracy pressure cannot halt the collapse. Nothing can. The core continues to compress, falling inward at a significant fraction of the speed of light. Within milliseconds, the entire core collapses to within its Schwarzschild radius. An event horizon forms. A singularity develops. A black hole is born. The outer layers of the star, initially left behind by the rapidly collapsing core, come crashing down. In many cases, they bounce off the newly formed compact object or are blown away by the intense neutrino flux, creating a supernova explosion. In other cases, especially for the most massive stars, the outer layers fall directly into the black hole without much visible explosion, an event called a direct collapse. The newborn black hole immediately possesses all the features predicted by general relativity: a singularity, an event horizon, and a photon sphere. If the progenitor star was rotating, the black hole will be a Kerr black hole with an ergosphere and multiple photon spheres. If the star had a binary companion, the black hole may begin accreting matter, creating an accretion disk that glows with incredible intensity. Supermassive black holes, with masses of millions to billions of solar masses, likely formed through different mechanisms in the early universe. The exact processes remain a topic of active research, but possibilities include the direct collapse of massive primordial gas clouds, the growth of stellar mass seed, black holes through sustained accretion, and the mergers of many smaller black holes over cosmic time. Whatever their formation mechanism, all black holes obey the same physical laws. They all possess photon spheres at the characteristic radius determined by their mass and spin. The photon sphere of a supermassive black hole is vastly larger than that of a stellar mass black hole, but its qualitative properties are identical. A photon orbiting M87's black hole follows the same equations as a photon orbiting a black hole formed from a collapsed massive star. This universality is one of the profound insights of general relativity. Black holes are simple. Their external properties depend only on mass, charge, and spin. Everything else, all the complex structure and composition of the matter that fell in to create them, is lost behind the event horizon. The photon sphere is one expression of this simplicity, a geometric feature determined entirely by the black hole's fundamental parameters. To understand the photon sphere, we must first understand the structure of the black hole it surrounds. A black hole is not truly a hole or an object in the conventional sense. It's a region of space-time where gravity has become so extreme that the normal rules of physics break down. Let us examine its anatomy piece by piece. At the very center of a Schwarzschild black hole, according to general relativity, lies the singularity. This is a point of theoretically infinite density, where all the mass of the collapsed star has been compressed into zero volume. Here, the curvature of space-time becomes infinite. Our equations cease to make sense. The laws of physics, as we know them, cannot describe what happens at the singularity. This is deeply troubling to physicists. A singularity represents a failure of our theories, a place where the mathematics breaks down and produces nonsensical infinities. Most physicists believe that singularities do not actually exist in nature, that some undiscovered theory, perhaps a quantum theory of gravity, will eventually resolve these infinities and tell us what really happens at the center of a black hole. But for now, the singularity remains one of physics's great mysteries, hidden behind the event horizon where no observation can reach it. Speaking of the event horizon, this is arguably the defining feature of a black hole. The event horizon is not a physical surface. You couldn't touch it or stand on it. It's a boundary, a mathematical surface that divides the universe into two regions: the outside, from which escape is still possible, and the inside, from which nothing can ever emerge. The event horizon sits at the Schwarzschild radius we discussed earlier. At this boundary, the escape velocity equals the speed of light. Any object inside this radius would need to travel faster than light to escape, which special relativity tells us is impossible. Once you cross the event horizon, your future contains only one destination: the singularity. What makes the event horizon particularly strange, according to theoretical calculations, is that an observer crossing it wouldn't necessarily notice anything special at the moment of crossing. Based on what general relativity predicts, if you were falling into a sufficiently large black hole, you wouldn't feel any sudden change. You wouldn't hit a wall. You wouldn't pass through a membrane. The event horizon appears to be defined entirely by its consequences for the future, not by any immediate physical sensation. Of course, no observer has ever crossed an event horizon and reported back, so this remains a prediction we cannot directly verify. From the perspective of an outside observer, however, something very strange appears to happen. Due to the extreme gravitational time dilation near the event horizon, objects approaching the boundary seem to slow down. Light emitted from an infalling object gets stretched to longer and longer wavelengths, becoming redder and dimmer. The object appears to freeze, never quite crossing the horizon, fading from view over infinite time. Of course, from the infalling object's own perspective, the crossing happens in finite time, and they continue falling toward the singularity. This is one of many ways that black holes challenge our intuitions about time and observation. Black holes come in different sizes, classified primarily by their mass. Stellar mass black holes form from the collapse of massive stars. When a star with more than about 20 to 25 times the mass of our Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes, and if the remaining mass exceeds the Tolman-Oppenheimer-Volkoff limit of roughly 3 solar masses, nothing can halt the collapse. The matter falls inward and forms a black hole. These stellar mass black holes typically have masses between about 5 and 50 times that of the Sun. Their event horizons range from roughly 15 to 150 kilometers in radius. They populate our galaxy and others, sometimes revealing themselves through X-ray emissions when they accrete matter from companion stars. At the other extreme are supermassive black holes, monsters with masses ranging from millions to billions of solar masses. These cosmic leviathans lurk at the centers of most large galaxies, including our own Milky Way. Sagittarius A star, the supermassive black hole at our galactic center, has a mass of about 4.3 million solar masses and an event horizon roughly 12 million kilometers in radius, about 17 times the radius of the Sun. The supermassive black hole at the center of the galaxy Messier 87, the first black hole ever directly imaged, has a mass of about 6.5 billion solar masses. Its event horizon is comparable in size to our entire solar system. Between these extremes lie intermediate mass black holes with masses ranging from hundreds to hundreds of thousands of solar masses. These objects are more difficult to detect and study, and their formation mechanisms remain somewhat mysterious. They may form from the merger of stellar mass black holes or from the direct collapse of massive gas clouds in the early universe. Understanding these different mass scales is crucial for understanding the experience of approaching a black hole, as we'll explore. Later, the tidal forces near a stellar mass black hole are far more violent than those near a supermassive black hole. Paradoxically, falling into a larger black hole can be, in some sense, gentler than falling into a smaller one. The variety of black holes in the universe is remarkable. Astronomers have now detected black holes across an enormous range of masses and environments. Stellar mass black holes have been discovered in X-ray binary systems, where they accrete matter from companion stars and emit characteristic high-energy radiation. Gravitational wave detectors have revealed black holes with masses up to about 150 solar masses, possibly formed through the merger of smaller black holes. Supermassive black holes have been identified at the centers of galaxies through their gravitational effects on nearby stars, through the energetic emissions from their accretion disks, and through direct imaging by the Event Horizon Telescope. Each of these black holes possesses a photon sphere. The photon sphere of a stellar mass black hole in an X-ray binary is only tens of kilometers in radius, yet it governs how light from the accretion disk reaches our telescopes. The photon sphere of a supermassive black hole at a galactic center extends millions of kilometers, influencing how we perceive the brilliant quasars that shine across the observable universe. The detection of gravitational waves from black hole mergers has provided a new way to study these objects. When two black holes spiral together and merge, they emit gravitational waves that carry information about their masses, spins, and the dynamics of the merger. The LIGO and Virgo detectors have observed dozens of such events since the first detection in 2015. Gravitational waves probe the strong field region of general relativity directly. The waves are generated in the region very close to the merging black holes, where spacetime curvature is most extreme. The waveform depends on the properties of the black holes, including features related to their photon spheres. The late stages of a merger, when the remnant black hole settles down to equilibrium, produce gravitational waves whose frequencies are connected to the properties of the newly formed photon sphere. The combination of electromagnetic observations, like those from the Event Horizon Telescope, and gravitational wave observations, provides complementary information about black holes. Electromagnetic observations reveal the structure of matter near black holes, including accretion disks, jets, and the bent light that forms the photon ring. Gravitational wave observations reveal the dynamics of spacetime itself, the ripples in the fabric of the universe caused by accelerating masses. Together, these observations are testing general relativity with unprecedented precision. So far, the theory has passed every test. The images from the Event Horizon Telescope match the predictions of general relativity for the shadow and photon ring of a supermassive black hole. The gravitational wave signals from black hole mergers match the predictions for the inspiral, merger, and ring-down phases. The photon sphere, predicted by Schwarzschild over a century ago, has been confirmed as a real feature of black holes in our universe. Now we arrive at the heart of our journey, the photon sphere itself. This is one of the most extraordinary structures in the cosmos, a region where light can become trapped in orbit, where the interplay between gravity and the nature of electromagnetic radiation creates phenomena that seem almost magical. The photon sphere exists at a very specific distance from a non-rotating black hole, exactly 1.5 times the Schwarzschild radius, or 3 times the quantity gm divided by c squared. For any black hole, regardless of its mass, the photon sphere sits at this precise ratio relative to the event horizon. Let's calculate some numbers to make this concrete. For a stellar mass black hole of 10 solar masses, the Schwarzschild radius is approximately 29.5 kilometers. The photon sphere, therefore, sits at about 44.3 kilometers from the center. For Sagittarius A star, with its 4.3 million solar masses, the event horizon radius is about 12.7 million kilometers, and the photon sphere is at roughly 19 million kilometers. For M87's supermassive black hole, the photon sphere lies approximately 29 billion kilometers from the center, nearly 10 times the distance from the Sun to Pluto. But why does the photon sphere exist at this particular radius? The answer lies in the balance between gravity's pull and the geometry of orbital motion. Consider a photon traveling near a black hole. Due to the curvature of space-time, the photon's path bends toward the black hole. If the photon is far away, the bending is slight, and the photon sails past the black hole, deflected but escaping to infinity. If the photon is too close, the bending is so severe that the photon spirals inward and crosses the event horizon, lost forever. But at exactly 1.5 times the Schwarzschild radius, something remarkable happens. At this distance, a photon traveling perpendicular to the radial direction, tangent to a circle centered on the black hole, experiences exactly the right amount of bending to maintain a circular path. The photon orbits the black hole like a planet orbits the sun, except at the speed of light. This is the only radius at which such circular photon orbits are possible. Inside this radius, the curvature is too strong, and photons cannot maintain circular orbits. They spiral in. Outside this radius, the curvature is too weak, and photons escape. However, and this is crucial, these circular orbits are unstable. Think of it like balancing a ball on the peak of a hill. A ball placed precisely at the top might stay there momentarily, but the slightest perturbation will send it rolling down one side or the other. Similarly, a photon in the photon sphere is in an unstable equilibrium. Any tiny perturbation, any slight deviation from the perfect circular path will cause the photon to either spiral into the black hole or escape to infinity. This instability means that photons don't remain in the photon sphere forever. Some fraction of those that enter with just the right trajectory might orbit the black hole 1, 2, or perhaps several times before eventually escaping or falling in. The photon sphere is not a permanent prison, but a transient limbo, a holding pattern where light can briefly linger before its ultimate fate is decided. The photon sphere would create remarkable visual phenomena based on what general relativity predicts. Imagine if it were somehow possible, standing at this radius and looking outward, away from the black hole. What would you see? Calculations suggest that due to the extreme gravitational lensing, the entire external universe would appear compressed into a bright band circling around you. Light from stars, galaxies, and nebulae that would normally come from all directions gets bent and concentrated, as if the cosmos itself were being squeezed through a cosmic funnel. Now imagine looking tangentially along the direction of the photon sphere. Here, theory indicates you might see something truly bizarre. Light from behind your own head. A photon emitted from the back of your head could, in principle, orbit the black hole and return to your eyes, allowing you to see yourself from behind. This boomerang effect, as some physicists call it, demonstrates just how radically spacetime would be curved at this location. Looking toward the black hole, you would see the event horizon, a perfect circle of absolute darkness. No light emerges from beyond this boundary, but surrounding this darkness would be a bright ring, the photon ring, created by photons that have orbited the black hole one or more times before escaping toward your eyes. This ring is extraordinarily thin and bright, carrying information about the extreme gravitational environment. In fact, there are theoretically an infinite number of such rings nested inside each other, corresponding to photons that have orbited once, twice, 3 times, and so on before escaping. Each successive ring is thinner, fainter, and closer to the edge of the black hole's shadow. These nested rings encode information about the space-time geometry very close to the event horizon, making them valuable targets for future observations. The photon sphere also exhibits a counterintuitive property related to what physicists call centrifugal force. Outside the photon sphere, the faster you orbit, the greater the outward centrifugal force you feel, just as you'd expect from your experience on a merry-go-round. At the photon sphere itself, this centrifugal force vanishes entirely. And inside the photon sphere, the relationship reverses. The faster you orbit, the stronger the inward force you experience. This reversal has profound implications for anything attempting to orbit or hover near a black hole. One of the most beautiful predictions of general relativity is gravitational lensing, the bending of light by massive objects. We touched on this earlier with Eddington's observations, but near black holes, this effect reaches its extreme expression. The photon sphere is intimately connected to the phenomenon of gravitational lensing, and understanding one helps illuminate the other. In flat spacetime, light travels in straight lines, but spacetime near massive objects is not flat. It's curved, warped by the presence of mass and energy. Light follows the shortest available paths through this curved geometry, which means that light rays bend around massive objects. The stronger the gravity, the more pronounced the bending. For the sun, the maximum deflection of starlight grazing its surface is about 1.75 arcseconds, a tiny angle barely detectable with the most sensitive instruments. For a galaxy cluster containing thousands of trillions of solar masses, the bending can be dramatic enough to create multiple images of background galaxies, stretched and distorted into arcs. When the alignment between a distant light source, a massive lens, and an observer is nearly perfect, something extraordinary happens. The light from the background source can bend around the lensing mass equally in all directions, creating a ring of light called an Einstein ring. This phenomenon was first discussed mathematically by the Russian physicist Orest Kvolson in 1924, and later quantified by Einstein himself in 1936. Einstein was initially skeptical that gravitational lensing would ever be observed, calling his 1936 paper a result that Rudy Mandel squeezed out of me, and saying it was of little value. How wrong he was. Today, gravitational lensing is one of the most powerful tools in modern astronomy, used to detect dark matter, measure cosmic distances, and even discover exoplanets. Astronomers distinguish several types of gravitational lensing based on the strength of the effect. Strong lensing occurs when light passes very close to a massive object, causing highly distorted images, multiple images, or Einstein rings. Weak lensing involves more subtle distortions, statistical stretching of galaxy shapes that can be detected only by analyzing many galaxies together. Microlensing occurs when a compact object, like a star or black hole, briefly passes in front of a more distant star, causing a temporary brightening. The most spectacular examples of strong lensing come from massive galaxy clusters. The Hubble Space Telescope has captured stunning images of blue arcs and rings surrounding these cosmic titans, where the light of distant galaxies has been bent and magnified. In some cases, the same galaxy appears multiple times at different positions around the cluster, each image showing the galaxy at a slightly different time due to the different path lengths the light has traveled. Near black holes, gravitational lensing reaches its most extreme form. The photon sphere represents the ultimate limit. Light bent into complete circles. Any photon that ventures inside the photon sphere and doesn't fall directly into the black hole will have its path curved by more than 90 degrees. Light from directly behind the black hole can be bent all the way around and sent toward a distant observer, creating part of the black hole's photon ring. The first direct image of a black hole, released by the Event Horizon Telescope collaboration in April 2019, shows this effect beautifully. The image depicts M87's supermassive black hole surrounded by a bright ring of emission. This ring is not the photon sphere itself, but the combined light from the hot accretion disk swirling around the black hole, bent and amplified by gravitational lensing. Embedded within this broader emission, too faint and thin to resolve clearly in the initial images, is the true photon ring formed by light that has orbited the black hole. The shadow at the center of the image, the dark region surrounded by the bright ring, is approximately 2.6 times the radius of the event horizon. This apparent size, larger than the event horizon itself, results from gravitational lensing. Light rays that would just barely skim the photon sphere get bent so severely that they never reach the observer. Instead, they're captured by the black hole. The result is a dark shadow that appears larger than the event horizon. Gravitational lensing has practical astronomical applications far beyond studying black holes. Because the bending of light depends on mass, but not on whether that mass is visible, gravitational lensing can reveal the presence of dark matter, the mysterious substance that makes up about 27% of the universe's total mass energy, but emits no light. By carefully measuring how galaxy clusters distort the shapes of background galaxies, astronomers can map the distribution of mass in the cluster. These maps consistently show that the visible matter, the galaxies themselves, accounts for only a small fraction of the total mass. The rest is dark matter, distributed in vast halos around and between the visible galaxies. Gravitational lensing has also been used to measure the expansion rate of the universe and to probe the nature of dark energy, the even more mysterious phenomenon driving the accelerating expansion of space. When a background quasar is multiplied, imaged by a foreground galaxy, light reaching each image travels along a different path with a different length. Any variability in the quasar's brightness appears at different times in the different images. By measuring these time delays and modeling the lens geometry, astronomers can estimate the Hubble constant, the rate at which the universe expands. Recently, researchers have even used gravitational lensing to detect molecules in a distant galaxy. The gravitational magnification allowed observations that would otherwise be impossible, revealing the chemical composition of a galaxy billions of light years away. So far, we have discussed primarily non-rotating black holes, described by the Schwarzschild solution. But nature rarely produces perfect stillness. Stars rotate, and when they collapse to form black holes, they carry their angular momentum with them. Most real black holes in the universe are spinning, some at tremendous rates. These rotating black holes are described by a different solution to Einstein's equations, discovered by New Zealand mathematician Roy Kerr in 1963. The Kerr solution is significantly more complex than the Schwarzschild solution, and it reveals that rotating black holes have additional features not present in their non-rotating cousins. Understanding these features helps us appreciate the full richness of black hole physics and the variety of phenomena that can occur near these cosmic objects. A rotating black hole possesses angular momentum quantified by a parameter called the spin. This spin can range from 0, recovering the Schwarzschild case, to a maximum value equal to the black hole's mass times the speed of light. A black hole spinning at this maximum rate is called an extremal Kerr black hole. Real astrophysical black holes have been measured with spins approaching, but not quite reaching, this maximum value. One of the most distinctive features of a Kerr black hole is the ergosphere. This is a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Within the ergosphere, it is impossible for any object to remain stationary relative to the distant stars, no matter how powerful its rockets. Space-time is rotating so rapidly that everything, including light, must move in the direction of the black hole's spin. The ergosphere is bounded by the static limit, an oblate spheroidal surface that touches the event horizon at the poles and extends farther out at the equator. At the poles, where there is no rotation, the static limit coincides with the event horizon. At the equator, it reaches out to twice the gravitational radius. Within the ergosphere, something remarkable becomes possible. Through a process called the Penrose process, it is theoretically possible to extract energy from a rotating black hole. An object falling into the ergosphere can split into two pieces, with one piece falling into the black hole and the other escaping with more energy than the original object had. The extra energy comes from the black hole's rotational energy. Over time, repeated use of the Penrose process could slow down the black hole's spin, converting its rotational energy into useful work. The Penrose process has been proposed as a possible explanation for some of the most energetic phenomena in the universe, including gamma-ray bursts and the powerful jets emanating from active galactic nuclei. A variation called the Blandford-Znajek process, which involves magnetic fields threading through the ergosphere, is considered the most likely mechanism for launching the relativistic jets observed in many supermassive black holes. For our purposes, the most relevant consequence of black hole rotation concerns the photon sphere, or rather the photon spheres, plural. A Kerr black hole does not have a single photon sphere, but infinitely many, lying between inner and outer limits that depend on the black hole's spin. Consider photons approaching a rotating black hole. A photon traveling in the same direction as the black hole's spin, moving with the rotation, experiences frame dragging that helps it maintain a circular orbit at a smaller radius. A photon traveling opposite to the spin, against the rotation, fights against the frame dragging and can only orbit at a larger radius. Photons approaching from polar directions parallel to the rotation axis have no preferred spin alignment and orbit at an intermediate radius. For a non-rotating black hole, all photon spheres coincide at 1.5 times the Schwarzschild radius. As the spin increases, the inner and outer photon sphere limits separate, with the inner limit shrinking toward the event horizon for prograde, co-rotating photons, and the outer limit expanding for retrograde, counter-rotating photons. In the extreme case of a maximally spinning black hole, a photon orbiting in the prograde direction can circle the hole at a radius equal to the event horizon itself. The photon sphere and event horizon nearly coincide for these co-rotating photons. Meanwhile, retrograde photons must orbit at 4 times the gravitational radius, significantly farther out. This has profound implications for what we would observe near a rotating black hole. The black hole's shadow, the dark region caused by light capture, becomes asymmetric. One side appears slightly flattened due to frame dragging, while the other bulges outward. The degree of asymmetry depends on the black hole's spin and the observer's viewing angle. By carefully measuring the shape of a black hole's shadow, astronomers can, in principle, determine its spin. The shadow of a Kerr black hole is not a perfect circle, but a slightly flattened shape, often described as a D shape or a cardioid. The degree of flattening depends on the black hole's spin parameter and the angle from which it is viewed. For an observer looking along the rotation axis, the shadow appears circular. For an observer in the equatorial plane, the asymmetry is most pronounced. The event horizon, telescope's observations of M87's black hole, show a shadow that is consistent with a spinning black hole, though the precise spin value remains uncertain due to limitations in the current resolution and the complexity of the surrounding emission. Future observations with improved telescope arrays and analysis techniques should provide more precise measurements. Understanding the spin of supermassive black holes is important for understanding how these objects formed and evolved. A black hole formed from the collapse of a single rotating star might have a specific spin related to the star's original rotation. A black hole that has grown through sustained accretion from a disk might have spun up or spun down, depending on the geometry of the accretion. A black hole that has grown through mergers with other black holes might have a spin influenced by the angular momenta of the merging objects. The spin of a black hole also affects the properties of the jets that many active black holes produce. The Blanford-Zinajek mechanism, thought to power these jets, depends on the black hole's spin and the magnetic fields threading through the ergosphere. Measuring the spin of black holes with jets can test our understanding of these energetic phenomena. The Event Horizon Telescopes. Observations of M87's black hole show slight asymmetries consistent with rotation, though the spin value remains somewhat uncertain. Future observations with improved resolution may allow more precise measurements. Frame dragging also causes photon orbits to precess. A photon starting from the north polar axis with zero angular momentum will orbit the black hole and return to the axis, but not to exactly the same point. Its orbit will have rotated slightly around the black hole. For certain specific values of the spin parameter, this precession can cause the photon to return precisely to its starting point after one or more orbits, creating what physicists have called photon boomerangs. One particularly elegant calculation showed that for a black hole spinning at approximately 99.434% of its maximum rate, a photon sent out from the north polar axis will orbit the black hole and return to its exact starting position. This remarkable behavior illustrates the intricate dance between gravity and light in the strongly curved spacetime around rotating black holes. What would it actually feel like to approach a black hole? What would you see? What would you experience as you fell toward one of these cosmic abysses? The answers depend critically on the black hole's size and on your reference frame, whether you're a distant observer watching someone else fall in, or the intrepid explorer falling in yourself. Let's start with time dilation, one of the most counterintuitive effects predicted by general relativity. Near a massive object, time passes more slowly. This effect, called gravitational time dilation, has been confirmed by numerous experiments, from the Hafele-Keating experiment that flew atomic clocks on airplanes to the precise corrections necessary for GPS satellites to function accurately. Near a black hole, time dilation becomes extreme. Imagine a clock positioned at various distances from a black hole while a distant observer watches. As the clock approaches the event horizon, the distant observer sees it tick more and more slowly. Light emitted by the clock gets stretched to longer wavelengths, a phenomenon called gravitational redshift. The clock appears to redden and dim. At the event horizon itself, from the distant observer's perspective, time stops completely. The clock appears to freeze, never quite crossing the boundary. Any object falling into a black hole seems to hover at the event horizon for eternity, becoming dimmer and redder until it fades from view. But from the clock's own perspective, nothing special happens at the event horizon. Time continues to flow normally. The clock crosses the horizon in finite time and continues falling toward the singularity. The discrepancy arises because the two observers are measuring different things. The distant observer is tracking coordinate time, defined by their position far from the black hole. The falling clock measures proper time, its own experience duration. Both are valid measurements, but they give dramatically different results. Now consider what the visual experience of falling toward a black hole might be like based on our theoretical understanding. As you approach, gravitational lensing would increasingly distort your view of the universe. Stars behind the black hole would have their light bent around it, creating multiple images. Stars to the side would appear displaced from their true positions. Simulations suggest the entire sky would seem to compress, squeezing into an ever smaller region behind you as you fall. At the photon sphere, if you could somehow hover there, you would likely see the universe compressed into a bright band around your equator. Looking directly away from the black hole, you would see multiple distorted images of the same stars, caused by light bending different amounts depending on how close it passed to the photon sphere. Looking toward the black hole, you would see the black shadow of the event horizon, surrounded by the bright photon ring. As you cross inside the photon sphere and continue falling, calculations indicate the sky would continue to compress behind you. The black hole's shadow would grow, swallowing more and more of your field of view. Eventually, the shadow would fill nearly your entire forward view, with the remaining universe visible only as a shrinking bright ring behind you. Then there are the tidal forces, the stretching and squeezing caused by the difference in gravitational pull between different parts of your body. Your feet, if they're closer to the black hole, experience stronger gravity than your head. This differential pull stretches you along the radial direction while simultaneously squeezing you from the sides. The strength of tidal forces depends on how rapidly gravity changes over the length of your body, which in turn depends on the black hole's mass. Near a stellar mass black hole, tidal forces become lethal well outside the event horizon. An astronaut falling toward a 10 solar mass black hole would be torn apart, stretched into a thin thread of matter, in a process that physicists colorfully call spaghettification. The tidal forces at the event horizon of such a black hole are billions of times stronger than what a person experiences standing on Earth's surface. But supermassive black holes tell a different story. Because they're so much larger, the gravitational gradient at the event horizon is much gentler. At the event horizon of Sagittarius A star, the tidal force on a person would be barely noticeable, weaker than what they'd experience on Earth. An astronaut could, in principle, cross the event horizon of a sufficiently large, supermassive black hole without feeling any unusual stretching or squeezing. This creates a strange paradox. Larger black holes would be, in some sense, more survivable than smaller ones, at least for the initial approach. Of course, once inside the event horizon, according to general relativity, the astronauts' fate would be sealed. They would eventually encounter tidal forces strong enough to destroy them as they approach the singularity. The larger the black hole, the longer this process would take, but the end result would be the same, assuming our current understanding holds true. Stephen Hawking popularized the term spaghettification in his book, A Brief History of Time, describing how an astronaut falling into a black hole would be stretched like spaghetti. But there's another possible fate: near supermassive black holes, where tidal forces squeeze rather than stretch at certain orientations. An infalling object might be compressed like a pancake rather than stretched like pasta. Astronomers have even observed tidal disruption events, where stars venturing too close to supermassive black holes are torn apart by tidal forces, creating bright flares as the stellar debris spirals inward. What happens after crossing the event horizon remains, by definition, forever hidden from outside observers. General relativity predicts that the infalling traveler will reach the singularity in finite proper time, experiencing increasingly violent tidal forces along the way. But whether the singularity truly exists, or whether some quantum gravitational effect intervenes, remains one of the deepest unsolved problems in physics. For most of human history, black holes remained theoretical curiosities, mathematical solutions that most physicists doubted corresponded to real objects in nature. Even as late as the 1960s, many experts believed that some unknown physical mechanism would prevent matter from collapsing to within its Schwarzschild radius. Today, we not only know that black holes exist, we have photographed them. The Event Horizon Telescope is not a single telescope, but a network of radio observatories spanning the globe. By coordinating observations from facilities in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica, astronomers effectively created a telescope the size of Earth. This technique, called very long baseline interferometry, achieves an angular resolution fine enough to read a newspaper in New York from a cafe in Paris. The EHT collaboration set out to image two targets: Sagittarius A star, the supermassive black hole at the center of our Milky Way, and M87 star, the even more massive black hole at the heart of the galaxy Messier 87, located about 55 million light-years away. On April 10, 2019, the collaboration released the first ever image of a black hole's shadow, M87 star. The image showed a bright, asymmetric ring of emission surrounding a dark central region. This ring corresponds to hot gas swirling around the black hole, its light bent and magnified by gravitational lensing. The dark center is the black hole's shadow, the region from which no light can escape to reach the telescope. The image matched the predictions of general relativity with remarkable precision. The ring's diameter agreed with theoretical expectations based on the black hole's estimated mass. The asymmetry with one side of the ring appearing brighter than the other results from relativistic beaming. Gas moving toward us gets its emission boosted, while gas moving away is dimmed. This asymmetry indicates that the black hole is rotating and that we are viewing it somewhat edge-on. 3 years later, on May 12, 2022, the collaboration released an image of Sagittarius A star. This image was actually harder to produce than the M87 star image. even though Sagittarius A star is much closer. The problem is that Sagittarius A star is also much smaller, and the gas around it changes on much shorter timescales. While the emission around M87 star remains relatively stable over days, allowing multiple observations to be combined, the emission around Sagittarius A star varies significantly over hours or even minutes. The collaboration had to develop new techniques to handle this variability and extract a stable underlying structure. The Sagittarius A star image shows a similar ring and shadow structure to M87 star, confirming that both objects behave as general relativity predicts for supermassive black holes. The ring diameter corresponds to a mass of about 4 million solar masses, consistent with previous estimates based on the orbits of stars near the galactic center. But the collaboration wanted to go further. Embedded within the broad emission ring should be a thin, bright feature, the photon ring, caused by light that has orbited the black hole one or more times before escaping. Detecting this photon ring would provide a direct probe of space-time very close to the event horizon. The visual distortions near a black hole have been simulated in remarkable detail using computer graphics and numerical relativity. These simulations show what an observer would see as they approach a black hole, accounting for all the effects of gravitational lensing, redshift, and relativistic beaming. Perhaps the most famous such simulation appeared in the 2014 film Interstellar, created under the scientific guidance of physicist Kip Thorne. The black hole, Gargantua, depicted in the film, was rendered using equations derived from general relativity. The result was an image that, while artistically enhanced for cinematic effect, captured the essential features predicted by physics: the dark shadow, the bright photon ring, the distorted appearance of the accretion disk visible above and below the black hole. Due to extreme gravitational bending, these simulations provide our best theoretical understanding of how profoundly our visual experience would be altered near a black hole. Based on these calculations, standing at the photon sphere, you would see the familiar sky transformed beyond recognition. Stars would appear displaced from their true positions, their light curved by the warped space-time. Multiple images of the same star could appear at different positions, some brighter and some dimmer, depending on the magnification caused by gravitational lensing. The black hole's shadow would dominate your view when looking toward it. This shadow represents not merely the absence of light, it would be a window into the void, a region where space-time curvature prevents any light from reaching your eyes. The edge of the shadow near the photon sphere would appear as a bright ring, the lensed light from the universe behind you, bent all the way around the black hole. If you were moving relative to the black hole, additional effects would appear. Light from the direction you were moving toward would be blue shifted, compressed to higher frequencies, and appearing brighter and bluer. Light from behind you would be red shifted, stretched to lower frequencies and appearing dimmer and redder. This relativistic beaming is the same effect observed in the asymmetric brightness of the photon ring in the Event Horizon Telescope images. The experience of time would also be peculiar. Your own subjective experience of time would continue normally, but if you could somehow observe distant clocks, they would appear to run fast, their ticking accelerated by the gravitational time dilation. The universe outside would seem to age rapidly compared to you. Conversely, an outside observer watching you would see your movements slowed, your clocks ticking sluggishly, as you approached the event horizon. These visual and temporal effects are not merely theoretical curiosities. They have real consequences for observations of black holes and their environments. The spectra of light from matter falling into black holes show characteristic gravitational redshifts. The dynamics of accretion disks are influenced by the varying rates of time passage at different distances from the black hole. The photon ring itself is a visual manifestation of the extreme gravitational bending that defines the photon sphere. In August 2022, a subset of the EHT team announced they had detected evidence of a photon ring in the M87 star data. By applying new analysis techniques to separate the diffuse emission from the sharper photon ring, they claimed to have resolved this elusive feature. However, other members of the collaboration disputed the claim, and the detection remains controversial. The photon ring, if present in the current data, is at the edge of detectability. Future improvements to the EHT, including adding more telescopes to the array and potentially placing dishes in space, will increase resolution and sensitivity. The next generation EHT and proposed space-based missions, like the Black Hole Explorer, aim to clearly resolve the photon ring and potentially detect the nested subrings predicted by theory. Each subring corresponds to photons that have orbited a different number of times, and together they encode information about space-time geometry very close to the event horizon. These observations have implications beyond mere curiosity. Certain theories attempting to resolve the black hole information paradox, the apparent conflict between quantum mechanics and general relativity regarding what happens to information that falls into a black hole, predict modifications to the photon sphere. If the event horizon has additional structure, perhaps a firewall of high-energy particles or a fuzzball replacing the classical horizon, these modifications might affect the width and brightness of the photon ring. Future observations could potentially distinguish between classical general relativity and these exotic alternatives. The photon sphere also connects to fundamental questions about the nature of spacetime itself. According to general relativity, spacetime is smooth and continuous, but many approaches to quantum gravity suggest that at very small scales, spacetime has a discrete structure, perhaps a foamy quantum texture. This discrete structure might affect the propagation of light in subtle ways, potentially observable in the fine details of photon ring images. We have traveled far tonight, from the nature of light itself to the geometry of spacetime, from the trenches of World War I to the radio dishes spanning our planet. We have explored the photon sphere, that strange boundary where light can orbit a black hole, trapped in an unstable equilibrium between falling in and escaping. The photon sphere reminds us that the universe operates by rules far stranger than our everyday experience suggests. Light, the fastest and freest thing in existence, can be captured by gravity so intense that even it cannot escape. Space and time, which seem so fixed and absolute in our daily lives, are actually malleable, bent and stretched by the presence of mass and energy. And yet, despite their strangeness, these phenomena are now observable. We have photographed the shadows cast by black holes. We have detected the ripples in space-time caused by their collisions. We are on the verge of directly imaging the photon ring, a feature that exists only because light can orbit these cosmic monsters. Consider what this means. A century ago, Carl Schwarzschild calculated the properties of black holes from a battlefield, and most physicists considered his results to be mathematical curiosities with no physical relevance. Today, we can image black holes across tens of millions of light years, confirming his predictions with extraordinary precision. The human capacity for understanding has grown to encompass phenomena that would have seemed purely fantastical to previous generations. The photon sphere exists right now, around every black hole in the universe, around stellar mass black holes scattered throughout galaxies, around the supermassive black holes anchoring galactic centers, around black holes we haven't discovered yet, lurking in the darkness between stars. Countless photons are circling these cosmic drains, some destined to escape and carry information to distant observers, others fated to eventually spiral in and vanish beyond the event horizon. Some of those escaping photons may eventually reach Earth. They will carry information about environments we can barely imagine, space-time curvatures that would destroy any physical object, gravitational fields that bend the very nature of reality. By capturing and analyzing this light, we learn about the universe at its most extreme. As you rest tonight, as your mind drifts toward sleep, consider the photon sphere. Consider light, the fastest thing in existence, forced to orbit a collapsed star. Consider the thin boundary between escape and eternal capture. Consider the mathematicians and physicists who predicted these phenomena decades before we could observe them, working with nothing but pencil, paper, and the power of human thought. The universe is vast and strange and beautiful, and we are privileged to live in an age when we can begin to understand its deepest secrets. The photon sphere is one such secret, a place where the familiar rules break down and new physics emerges. If you've enjoyed this journey into the mysteries of the cosmos, if these nocturnal explorations help you find peace and wonder at the edge of sleep, please consider liking and subscribing to the channel. Your support makes these expeditions possible. Until next time, let the darkness comfort you rather than frighten you. Remember that even in the darkest regions of space, around the most extreme objects in existence, light continues to dance its eternal dance. The photon sphere proves that even when gravity seems to have won, even when escape seems impossible, light finds a way to circle, to orbit, to persist. Rest well, knowing that you are part of a universe capable of producing such marvels. Rest well, knowing that human minds can grasp such distant and strange phenomena. Rest well, knowing that the same gravity that holds you gently to your bed extends throughout the cosmos, shaping galaxies, forming black holes, and bending light into the circular paths of the photon sphere. Good night, and may your dreams take you to the edge of physics, where light cannot escape and wonder has no bounds. But before sleep claims you entirely, let us linger a moment longer in the company of these cosmic marvels. There is still more to explore, more connections to draw, more wonder to contemplate. The photon sphere connects to deep questions about the nature of information in our universe. Consider a photon orbiting in the photon sphere. This photon carries information about whatever process created it, perhaps the glow of hot gas falling toward the black hole, perhaps the dying light of a star torn apart by tidal forces. As the photon circles the black hole, where does that information reside? Is it in the photon itself, in the space-time through which it travels? In some more fundamental description we haven't yet discovered. These questions connect to what physicists call the holographic principle, a profound idea suggesting that all the information contained in a volume of space can be encoded on the boundary of that space. For black holes, this principle suggests that everything that falls past the event horizon is somehow encoded on the horizon itself. The photon sphere, lying just outside this boundary, represents a kind of liminal zone, a threshold between the ordinary universe where information flows freely and the interior of the black hole where information seems to become trapped or even destroyed. The photon sphere also invites us to contemplate the nature of observation itself. We understand the universe through the light that reaches our eyes and instruments, but near a black hole, light behaves so strangely that our ordinary intuitions about observation break down entirely. An observer at the photon sphere would see the universe in ways no human has ever experienced, compressed and distorted, with multiple images of the same objects, with light arriving from impossible directions. This raises a philosophical question. Is there an objective reality independent of observation? Or is reality, in some sense, constructed by the act of observing? Physics offers no definitive answer, but the bizarre behavior of light near black holes suggests that the relationship between observers and the observed universe is more complex than our everyday experience suggests. Consider the history of human understanding of light and gravity. For most of human history, these were considered entirely separate phenomena. Light was something that allowed us to see, produced by flames and reflected by surfaces. Gravity was the force that made objects fall and kept the moon in orbit. The idea that gravity could affect light would have seemed absurd to ancient philosophers and even to most scientists before Einstein. Newton himself speculated about whether gravity might bend light, reasoning that if light consisted of particles with some kind of mass, then gravitational attraction should deflect them. But without knowing the true nature of light, he could not calculate the effect. The French mathematician Pierre-Simon Laplace and the English natural philosopher John Michel independently considered, in the late 18th century, what would happen if an object were so massive and compact that light could not escape its gravitational pull. Michel, writing in 1783, described these objects as dark stars. He had no way to calculate their properties precisely, but his intuition was essentially correct. It took Einstein's general relativity to put these ideas on firm mathematical footing, and it took Schwarzschild's solution to reveal the specific predictions, the event horizon, the singularity, and yes, the photon sphere. These predictions lay dormant for decades, considered mathematical curiosities by most physicists. It wasn't until the theoretical work of Oppenheimer and Snyder in 1939, and especially the renaissance of general relativity in the 1960s, led by John Wheeler and others, that black holes were taken seriously as potential real objects. Wheeler, in fact, is credited with coining the term black hole in 1967, replacing the more cumbersome phrase gravitationally completely collapsed object. The name stuck, capturing something of the mysterious and forbidding nature of these cosmic phenomena. Wheeler also promoted the phrase, "A black hole has no hair," expressing the idea that black holes are characterized only by their mass, charge, and spin, with no other distinguishing features. Two black holes with identical mass, charge, and spin are absolutely identical, regardless of what fell in to create them. The photon sphere is one manifestation of this simplicity. Its radius depends only on the black hole's mass for non-rotating black holes, and on mass and spin for rotating ones. It doesn't matter whether the black hole formed from a collapsing star, from the merger of two smaller black holes, or from the direct collapse of a massive gas cloud in the early universe. Once formed, the black hole remembers nothing of its origin, and its photon sphere has exactly the same properties as any other black hole of the same mass and spin. This universality has profound implications. It means that by studying the photon sphere of any black hole, we learn about the fundamental properties of spacetime near all black holes. The observations made by the Event Horizon Telescope of M87's black hole tell us not just about that particular object, but about black holes in general, including the supermassive black hole at our own galactic center, too small and rapidly variable to image with current technology, but obeying the same laws. Let us delve deeper into the mathematics that governs the photon sphere. For a Schwarzschild black hole, the effective potential that determines photon trajectories can be written as a function of the radial coordinate. This potential has a maximum at exactly 3/2 times the Schwarzschild radius, the location of the photon sphere. A photon at this radius with zero radial velocity can remain in a circular orbit, but the orbit is unstable because the potential has a maximum there, not a minimum. The instability can be quantified. A photon at the photon sphere with a small perturbation will either escape to infinity or fall into the black hole on an exponentially growing trajectory. The characteristic time scale for this instability is related to the light crossing time of the black hole. For stellar mass black holes, this is measured in microseconds. For supermassive black holes, it can be hours or days. This instability explains why we don't see a bright, static ring of light at the photon sphere in observations. Photons don't linger there. They quickly escape or fall in. However, as photons scatter in the region near the photon sphere, some small fraction will temporarily enter orbits that pass close to this unstable circular orbit. These photons can wind around the black hole one or more times before their fate is determined. Each winding adds a delay and a specific angular displacement to the photon's trajectory. The collection of all these photons escaping after different numbers of windings creates the photon ring structure visible in theoretical simulations and increasingly in real observations. The nested subrings of the photon ring have a specific mathematical relationship. Each successive subring, corresponding to photons that have orbited one more time, is thinner and fainter by a factor related to the Lyapunov exponent of the unstable orbit. This factor is approximately 500 for a Schwarzschild black hole, meaning the second subring is about 500 times thinner and fainter than the first, and so on for higher subrings. This rapid decrease makes detecting the higher order subrings extremely challenging, but it also means that each subring provides independent information about the spacetime geometry near the photon sphere. One remarkable prediction involves the shape of the subrings for rotating black holes. While the overall photon ring shape depends on the viewing angle and the black hole's spin, the successive subrings become increasingly circular and increasingly dominated by photons that have orbited close to the equatorial plane. The inner subrings, therefore, provide information about the most extreme regions of spacetime closest to the event horizon. The photon sphere also plays a role in a phenomenon called quasi-normal ringing. When a black hole is perturbed, perhaps by matter falling in or by a gravitational wave passing by, it vibrates at characteristic frequencies determined by its mass and spin. These vibrations are called quasi-normal modes, and they decay over time as the black hole radiates gravitational waves and settles back to equilibrium. The frequencies and decay rates of quasi-normal modes are intimately connected to the properties of the photon sphere. The real part of the quasi-normal mode frequency, which determines the oscillation period, is related to the orbital frequency of photons at the photon sphere. The imaginary part, which determines the decay rate, is related to the instability of the photon sphere. This connection, discovered theoretically in the 1980s, provides a bridge between electromagnetic observations of the photon ring and gravitational wave observations of perturbed black holes. The LIGO and Virgo gravitational wave detectors have observed the ring-down phase of black hole mergers, when the newly formed merged black hole settles down to equilibrium while emitting gravitational waves. The frequencies observed are consistent with the predictions of general relativity for the quasi-normal modes. As gravitational wave detectors become more sensitive, they may be able to detect multiple quasi-normal modes and verify the detailed relationship with the photon sphere properties. Let us also consider what the photon sphere tells us about the possibility of exotic objects that might mimic black holes. Various theoretical proposals suggest alternatives to classical black holes, objects that might appear very similar from a distance, but have different internal structure. These include wormholes, gravastars, boson stars, and various quantum gravity-inspired objects. Many of these alternatives also possess photon spheres, because any sufficiently compact object will curve spacetime enough to create circular photon orbits. However, the detailed properties of the photon sphere, and especially the photon ring it produces, can differ between classical black holes and these alternatives. Some alternatives lack event horizons entirely, which means light can escape from their interiors, potentially creating additional rings or modifying the appearance of the central shadow. The photon ring therefore serves as a diagnostic tool for testing the nature of compact objects. If future observations reveal that the photon ring around a supposed black hole deviates from general relativistic predictions, this could indicate that the object is something other than a classical black hole. Conversely, increasingly precise agreement with general relativistic predictions strengthens our confidence that black holes exist and behave as Einstein's theory predicts. The Event Horizon Telescope collaboration has analyzed their M87 and Sagittarius A-star images to test general relativity. The results are consistent with the theory at the current level of precision, ruling out some alternative models, but not yet sensitive enough to distinguish between general relativity and some more subtle modifications. Future improvements to the telescope array and the development of space-based components will dramatically increase the power of these tests. Let us now contemplate the extremes that exist within our universe. Black holes represent the ultimate in gravitational compaction, but they are not the only extreme objects. Neutron stars, the collapsed cores of massive stars that didn't quite become black holes, also possess photon spheres if they are compact enough. A neutron star with sufficient mass and small enough radius can have a photon sphere outside its surface. Light passing close to such a neutron star can orbit around it, though the star itself remains visible at the center. The distinction between a neutron star with a photon sphere and a black hole involves the relationship between the object's physical radius and its Schwarzschild radius. For a black hole, the physical radius is less than the Schwarzschild radius, meaning the event horizon exists. For a neutron star, the physical radius is larger than the Schwarzschild radius, but might still be less than the photon sphere radius of 3/2 times the Schwarzschild radius. In this case, the neutron star has a photon sphere but no event horizon. Observations of such ultra-compact neutron stars would reveal fascinating phenomena. Light emitted from the stellar surface on the side, facing away from an observer, could bend around the star and reach the observer, creating multiple images of the stellar surface. Hot spots on the star could appear to warp and stretch as they rotate around. These effects have been studied theoretically and may be observable with future X-ray telescopes. The masses and radii of neutron stars are governed by the equation of state of matter at nuclear densities, physics that remains incompletely understood. Observations of neutron stars, including gravitational waves from neutron star mergers and X-ray emissions from neutron star surfaces, provide constraints on this equation of state. The presence or absence of photon spheres around the most massive neutron stars could provide additional constraints. Between neutron stars and black holes lies a region of uncertainty. What happens when a neutron star exceeds the maximum mass that can be supported against gravitational collapse? General relativity predicts that it must collapse to a black hole, but the details of this collapse involve quantum gravitational effects that remain poorly understood. Some theoretical proposals suggest the formation of exotic objects with properties intermediate between neutron stars and classical black holes. The photon sphere connects to another fascinating topic: time travel and closed time-like curves. In certain exact solutions of Einstein's equations, including some involving rotating black holes, spacetime contains paths along which an object could travel and return to its own past. These closed time-like curves raise profound paradoxes about causality and free will. The photon sphere, while not itself a time travel mechanism, illustrates how general relativity allows trajectories that seem impossible in flat spacetime. A photon completing a full orbit in the photon sphere travels through space in a closed loop. While this particular loop is through space rather than time, the geometry that makes it possible is closely related to the geometry that permits closed time-like curves in more exotic solutions. Most physicists believe that some mechanism, perhaps rooted in quantum gravity, prevents closed time-like curves from actually forming in realistic situations. Stephen Hawking formulated this belief as the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel. But the resolution of this conjecture remains unknown, and the extreme space-time curvature near black hole photon spheres provides one of the most relevant testing grounds for understanding these issues. The photon sphere also appears in the context of black hole thermodynamics, one of the most surprising developments in theoretical physics of the late 20th century. In the early 1970s, Jacob Bekenstein proposed that black holes possess entropy proportional to the area of their event horizons. Shortly thereafter, Stephen Hawking showed that black holes emit thermal radiation at a temperature inversely proportional to their mass, a phenomenon now known as Hawking radiation. These results established that black holes are thermodynamic objects possessing temperature and entropy and obeying laws analogous to the laws of thermodynamics. The entropy of a black hole is enormous, approximately 10 to the power of 77 for a solar mass black hole, far exceeding the entropy of any ordinary object of comparable mass. The photon sphere plays a subtle role in understanding black hole entropy. The entropy is proportional to the area of the event horizon, but the photon sphere provides a kind of outer boundary for the region of extreme spacetime curvature. Information about what fell into the black hole seems to be encoded somehow in this region, though the precise mechanism remains a subject of active research. The black hole information paradox, first articulated by Hawking in the 1970s and still unresolved today, asks what happens to information about objects that fall into a black hole. Quantum mechanics demands that information be conserved, but Hawking's calculation suggested that the EI's radiation emitted by a black hole carries no information about what fell in. If true, this would represent a fundamental violation of quantum mechanics. Various proposed resolutions to this paradox involve the structure of spacetime near the event horizon and photon sphere. Some proposals suggest that the event horizon is replaced by a more complex structure, perhaps a firewall of high-energy particles or a fuzzball of string theory. Others suggest that information escapes through subtle quantum correlations in the Hawking radiation. Still others propose that information remains inside the black hole until it evaporates completely, emerging only at the end. The photon sphere provides an observational window into these questions. If the event horizon has additional structure beyond what classical general relativity predicts, this structure might affect the photon ring in detectable ways. Future observations with sufficient precision could potentially distinguish between classical black holes and various quantum gravitational alternatives. Let us turn our attention to the role of black holes and their photon spheres in the broader context of cosmic evolution. Black holes are not merely curiosities. They are active participants in the evolution of the universe. Supermassive black holes at the centers of galaxies influence the evolution of their host galaxies in profound ways. When a supermassive black hole actively accretes matter, it releases enormous amounts of energy that can heat surrounding gas and suppress star formation. This feedback mechanism helps regulate the growth of galaxies and explains certain observed relationships between black hole masses and galaxy properties. The jets launched by accreting supermassive black holes can extend for millions of light years, carrying energy and momentum far beyond the host galaxy. These jets create enormous cavities in the hot gas that pervades galaxy clusters, affecting the thermal evolution of these largest, gravitationally bound structures in the universe. The photon sphere plays a role in the energetics of these processes. The energy extraction mechanisms proposed for powering jets, such as the Blandford-Zenojec process, involve electromagnetic fields threading through the ergosphere of a rotating black hole. The photon sphere marks the boundary within which these fields are most strongly influenced by the extreme spacetime curvature. In the early universe, supermassive black holes grew remarkably quickly. Observations of quasars at high redshift reveal that black holes with masses of billions of solar masses existed when the universe was less than 1 billion years old. How these black holes grew so large so quickly remains a puzzle. Various mechanisms have been proposed, including the direct collapse of massive primordial gas clouds, rapid mergers of smaller black holes, and sustained super-Eddington accretion. Whatever the mechanism, these early black holes possessed photon spheres, just as their modern counterparts do. Light emitted by the accretion disks around these primordial black holes was bent and lensed by the same physics we observe today. By studying the most distant quasars, we probe black hole physics across cosmic time and test whether general relativity holds in the early universe. Gravitational wave astronomy has opened a new window on black holes and their photon spheres. The LIGO and Virgo detectors have observed dozens of black hole mergers, events in which two black holes spiral together and coalesce into a single, larger black hole. These observations directly test general relativity in the strong field regime, where spacetime curvature is most extreme. When two black holes merge, their individual photon spheres merge as well. The final stage of the merger, the ring-down, represents the newly formed black hole settling into its equilibrium configuration, including the establishment of its photon sphere. The gravitational waves emitted during ring-down encode information about the final black hole's mass and spin, and through them, about its photon sphere. The LIGO collaboration has detected the ring-down phase of several mergers and verified that the observed frequencies match general relativistic predictions for quasi-normal modes. As detector sensitivity improves, more detailed tests will become possible, potentially revealing deviations from general relativity or confirming it with ever greater precision. Future gravitational wave detectors, including the space-based LISA mission planned for launch in the 2030s, will observe supermassive black hole mergers. These events involve black holes with masses of millions to billions of solar masses, much larger than the stellar mass black holes observed by LIGO. The ring-down of supermassive black hole mergers will provide tests of general relativity on entirely different scales, probing the photon spheres of the largest black holes in the universe. Contemplating the photon sphere invites reflection on the nature of extremes in physics. Why does the universe contain such extreme objects? What role do they play in the cosmic scheme? Black holes represent the endpoint of stellar evolution for the most massive stars. They are the ashes of cosmic fires, the remains of nuclear furnaces that have exhausted their fuel and collapsed under their own gravity. In this sense, black holes are inevitable consequences of the processes that create the heavy elements essential for life. Without massive stars, the universe would contain only hydrogen and helium, the elements created in the Big Bang. Without black holes, those massive stars would have no ultimate fate. The existence of black holes and their photon spheres is intimately connected to the existence of the chemical elements that compose our bodies and our world. Some theorists speculate about the role of black holes in even larger cosmic cycles. Could black holes be the seeds of new universes, regions of space-time that bud off from our universe and evolve independently? This idea, proposed by physicist Lee Smolin and others, suggests that black hole interiors might give rise to big bangs in separate spacetimes, creating baby universes that inherit some properties from their parent. These speculations remain highly theoretical, but they illustrate how the extreme physics of black holes connects to the deepest questions about cosmic origins and destiny. The photon sphere, marking the boundary of stable orbits, represents a kind of threshold between the comprehensible and the incomprehensible, between the universe we can observe and the regions forever hidden from us. As we conclude this extended journey, let us summarize the key insights we have gathered. The photon sphere is a spherical region at precisely 1.5 times the Schwarzschild radius of a non-rotating black hole, where the gravitational pull is exactly sufficient to bend light into circular orbits. These orbits are unstable, with photons quickly escaping or falling in after any small perturbation. For rotating black holes, multiple photon spheres exist at different radii for photons with different relationships to the black hole's spin. The photon sphere creates the photon ring observed in black hole images, a thin, bright feature surrounding the black hole's shadow. This ring consists of light that has orbited the black hole one or more times before escaping. Nested subrings corresponding to different numbers of orbits encode information about spacetime geometry very close to the event horizon. The existence of the photon sphere was predicted mathematically by Schwarzschild in 1916, confirmed observationally by the Event Horizon Telescope beginning in 2019, and represents one of the most extraordinary demonstrations of general relativity's predictive power. It connects to fundamental questions about the nature of light, gravity, space-time, information, and the structure of the universe. Now sleep approaches, and these weighty matters can rest. You have traveled far tonight, from the speed of light to the curvature of space-time, from the trenches of World War I to the radio telescopes of the 21st century. You have contemplated phenomena at the edge of physics, where matter and energy and space and time twist together in ways that challenge human intuition. Remember that you are part of this universe, this cosmos that contains black holes and photon spheres. The atoms in your body were forged in the same stellar processes that create black holes. The light that carries this information to your eyes obeys the same laws that govern light near event horizons. You're connected to these cosmic marvels by the deepest bonds of physics. Let this knowledge comfort you as you drift towards sleep. The universe is vast and strange and beautiful, and you are privileged to live in an age when its deepest secrets are beginning to yield to human understanding. The photon sphere awaits discovery by future generations of scientists and dreamers who will build on the work of Einstein and Schwarzschild and the Event Horizon Telescope to peer ever deeper into the mysteries of existence. If you've enjoyed this journey, please remember to like and subscribe. Your support allows these explorations to continue, bringing the wonders of the cosmos to those who seek understanding and peace in the contemplation of nature's grandest phenomena. Rest now. Let your thoughts orbit gently, like photons in the sphere, circling but not falling, balanced between the known and the unknown. Tomorrow brings new light, but tonight the darkness holds its own profound beauty. Sleep well, dear traveler. The universe keeps its vigil while you rest, its black holes spinning silently in the void, their photon spheres marking the boundaries between light and shadow, between what can be known and what must forever remain mystery. The photon sphere will continue to exist long after we are gone, billions of years from now, when our sun has swelled into a red giant and then faded into a white dwarf, when the Earth has been consumed or cast adrift, the black holes of the universe will persist. Their photon spheres will continue to capture and bend light, marking the boundary of the region where even photons must orbit. On longer timescales, still, through the process of Hawking radiation, even black holes will eventually evaporate. A stellar mass black hole takes far longer than the current age of the universe to evaporate, but given enough time, approximately 10 to the power of 67 years, it will radiate away all its mass and vanish. Supermassive black holes take even longer, perhaps 10 to the power of 100 years. But in the fullness of time, even the greatest black holes will fade. When a black hole evaporates, what happens to its photon sphere? As the black hole loses mass, its Schwarzschild radius shrinks, and its photon sphere shrinks with it. The characteristic properties of the photon sphere change, but it remains at 1.5 times the shrinking Schwarzschild radius. In the final moments before evaporation, when the black hole has shrunk to the Planck mass, quantum gravitational effects become important, and our current theories cannot describe what happens. The photon sphere, like the black hole itself, disappears in a final burst of Hawking radiation. This ultimate fate lies unimaginably far in the future, but it reminds us that even the most extreme objects in the universe are not eternal. The photon sphere exists now, around every black hole, a testament to the strange beauty of general relativity. But like everything in the physical universe, it too will pass. For now, let us be grateful for the opportunity to understand these phenomena. A few generations ago, black holes were mathematical curiosities, doubted by most physicists. Today, we photograph them. A few generations hence, we may observe them with even greater precision, resolving the photon ring and its subrings, testing general relativity and its alternatives with unprecedented accuracy. The human capacity for understanding has grown to encompass the most extreme environments in the cosmos. From our small planet, orbiting an ordinary star, in an unremarkable galaxy, we have reached out with mathematics and telescopes to grasp the nature of black holes and photon spheres. This is a remarkable achievement, worthy of contemplation as you drift towards sleep. The universe is vast, but our minds have proven capable of comprehending its vastness. The universe is strange, but our theories have proven capable of describing its strangeness. The photon sphere is one small piece of this vast puzzle, but understanding it connects us to the deepest questions about space, time, gravity, and the nature of reality. May these thoughts accompany you into sleep. May your dreams be filled with the wonder of the cosmos, and may you awaken refreshed, ready to face another day in this universe of marvels. Good night.